In this video, we are going to look at substitution reactions of alcohols. First, we should look at acid-base properties of alcohols. This is something that we have covered earlier in chapter 5. So alcohols, in terms of acid-base properties, are amphiporotic, similar to water. As you may recall, we consider alcohols, or we can look at alcohols, as molecule of water in which one hydrogen has been replaced by a hydrocarbon substituent. So an alcohol readily reacts with a base to donate a proton, and so it acts as an acid in reaction with the base, and the product is corresponding conjugate base and alkoxide. Alternatively, as shown in the second reaction, alcohol is a proton acceptor, and alcohol can act as a base to be protonated to the corresponding oxonium ion, which is a conjugate acid of the starting alcohol. Now we can look at substitution and elimination reactions of alcohols. So an alcohol can be protonated. Alcohol has a hydroxyl group, which is very poor leaving group. But upon protonation, it is converted into oxonium ion, and that oxonium ion is actually a rather good leaving group. You may recall from previous chapters, a poor leaving group is one that is a strong base. So hydroxyl group of alcohol upon leaving would be hydroxide, strong base, therefore poor leaving group. But upon protonation, we end up with oxonium ion. Upon leaving, it leaves as molecule of water, and that's weak base or a good leaving group. So remember this is a very common trick in organic chemistry. When we have a poor leaving group, or in general functional group that has low reactivity, we can convert it sometimes into more reactive group by protonation. And now reaction of the oxonium ion with the nucleophile may result in nucleophilic substitution, or reaction with the base may result in an elimination reaction. An important reaction, or more accurately reactions of alcohols, involve formation of corresponding alkyl halides from alcohols. Alcohols are inexpensive starting materials, usually readily available, and alkyl halides are more valuable intermediates or starting materials for organic synthesis, for preparation of other value-added compounds. So conversion of alcohols to alkyl halides is important synthetic transformation, and we have a number of methods to do it. The simplest method involves reaction of an alcohol with corresponding hydrogen halide. And here are some examples. So in the first example, reaction of methanol with hydrogen chloride gives corresponding chloride, that would be methyl chloride or chloromethane, and water is byproduct. In the second example, reaction of 2-butanol with hydrogen bromide results in formation of 2-bromobutane, and again, as you can see, water is byproduct. And in the final example, 1-methyl-cyclopentanol reacts with hydrogen iodide to give 1-iodo, 1-methyl-cyclopentane, and as in previous cases, water is the byproduct. A reaction may proceed by either SN1 or SN2 reaction mechanism. So tertiary and secondary alcohols react by SN1 reaction mechanism. We have to use, in this case, hydrogen halide as a source of halogen. We cannot use a salt of halogen like sodium chloride, sodium bromide, potassium iodide, because hydroxide is a poor leaving group and would not leave in a reaction with simply halide anion. That's why we have to use hydrogen halide. So hydrogen from hydrogen halide protonates hydroxyl group of an alcohol and converts it into a good leaving group. So that's the role of the acid. So halogen has to be part of the acid for reaction to occur. Now that we have a good leaving group, under SN1 reaction conditions, molecule of water leaves, all those are equilibrium reactions, and the intermediate carbocation is formed. Now this intermediate carbocation can react with nucleophile, and then product is corresponding alkyl halide. In this case, product would be 2-iodo 2-methyl-butane. Alternatively, molecule of water could act as a base and cause elimination But that's not a problem, because under these reaction conditions, now hydrogen halide adds to the resulting alkene following Markovnikov rule to give the same alkyl halide, 2-iodo-2-methylbutane. So in this case, same product may form by two different mechanisms, either directly by substitution or by elimination addition sequence. Of course, since carbocation is the reaction intermediate in SN1 reactions, rearrangements are common. Here is one example, starting with 3,3-dimethyl-2-butanol. Upon protonation, let's say in reaction with hydrogen bromide, upon protonation, oxonium ion is formed, and after loss of water, secondary carbocation is the reaction intermediate. Of course, tertiary carbocations are more stable than secondary, and so direct reaction of secondary carbocation with a nucleophile bromide anion to give the product 2-bromo-3,3-dimethyl-2-butane will only be the minor product. Depending on reaction conditions, yield may vary, but it's typically 3–4% of the reaction product. Major reaction pathway involves alkyl rearrangement of a methyl group. So one of the neighboring three methyl groups shifts, and result is formation of tertiary carbocation. Note that unlike other steps in this reaction mechanism, rearrangement is not a reversible step. So rearrangement from secondary to tertiary carbocation, from less to more stable carbocation, is not a reversible step. And now bromide anion reacts with rearranged resulting tertiary carbocation to give the final product, and that's the major product. So the major product is 2-bromo-2,3-dimethyl-butane. Methyl and primary alcohols, so methyl alcohol and primary alcohols, react with hydrogen halides by SN2 reaction mechanism. So SN2 reaction mechanism involves acid-base reaction as the first step, protonation, and that's not actually SN2 part of SN2 mechanism. It's simply acid-base reaction, a protonation. And then second step is actual SN2 reaction. So backside attack of the nucleophile results of in this case, formation of carbon-chlorine bond and breaking of carbon-oxygen bond, so molecule of water leaves as a leaving group. So note that while this is two-step reaction, SN2 reaction itself is not a two-step reaction. SN2 reaction is a concerted reaction. So two-step process involves first an acid-base reaction followed by SN2 reaction. Now, Lucas test for alcohols is a test that works both with alcohols that react through SN1 and those that react through SN2 reaction mechanism. It's actually a test that we won't do anymore. It's an obsolete test, but it has high educational value, and so we expect undergraduate students to know it. So a Lucas test involves reaction of an alcohol, as in this case, let's say 1-pentanol, with hydrogen chloride in aqueous solution of zinc chloride. So aqueous solution of zinc chloride and hydrogen chloride is called Lucas reagent. And test that uses Lucas reagent is called Lucas test. Products are corresponding alkyl halides, in this case 1-chloropentane. Reagent, Lucas reagent, so aqueous solution of hydrogen chloride and zinc chloride in water, is colorless, it's clear. The same goes for alcohols, they are also clear. When two are mixed, alcohols are supposed to be miscible with water, and only smaller alcohols, those up to about 5 or 6 carbon atoms, are soluble in water. Larger alcohols, when you get to 8 carbon atoms or more, solubility is very low, so test cannot be applied to them. So that's one of the limitations of the test. Only alcohols soluble in water can be used in this test. So when we mix Lucas reagent with alcohol soluble in water, initially clear solution forms. But products, reaction product, alkyl halide, alkyl chloride, is insoluble in water. As it separates, as it forms and separates from water, before it separates to make a separate layer, it forms emulsion in water. And that emulsion is non-transparent. It's basically cloudy. And it's so cloudy that one cannot see through that solution. So formation of opaque, cloudy solution that one cannot see through is positive test. And we time the reaction to see how long it takes for positive test to occur. So this is primary alcohol, this example of reaction of primary alcohol, and here is reaction mechanism. In this case, we use zinc 2+, so zinc 2+ cation as the electrophile to activate oxygen because it is actually stronger electrophile than proton, and it makes oxygen of the hydroxyl group even more electron deficient. It makes it into a better leaving group. So reaction occurs faster than if we were to carry out reaction as a simple protonation. Alternatively, we could heat up the reaction mixture, but these tests are carried out at room temperature. So use of zinc chloride allows us to carry out reaction at room temperature. So this is very good leaving group. And then, of course, backside attack in case of primary alcohols. Backside attack SN2 reaction results in formation of reaction product, in this case 1-chloropentane. So on primary alcohols, mechanism is SN2. On secondary and tertiary alcohols, Lucas test proceeds through SN1 reaction mechanism. And of course, those reactions are much faster. So tertiary alcohol reacts with Lucas reagent almost immediately. Reaction is typically completed in less than 1 minute. In case of secondary alcohol, reaction is completed within minutes, typically 5 to 10 minutes. It's very seldom that it will take more than 10 minutes, typically about 5 minutes. So you can see that reaction rate reflects relative stability of carbocations. Tertiary carbocation is more stable than secondary, which means it forms faster and reaction is correspondingly faster. This is noticeable difference in reaction rates, and so we can easily distinguish by timing the reaction and timing how long it takes for positive reaction to occur. We can easily distinguish primary, secondary, and tertiary alcohols, and primary alcohols actually take hours to react. So typically for a primary alcohol, we will leave that aside and check it after a while, after a few hours, to see if reaction has been completed. So before advent of spectroscopy, Lucas test was one of the tests that we used to determine degree of substitution of an alcohol. So remember this test. It frequently comes up on exams, including various standardized exams. So tertiary alcohols react almost instantaneously, typically in less than a minute, no more than a minute. Secondary alcohols take minutes, no more than 5 to 10 minutes. And primary alcohols take hours, 2 to 3 hours. Reactions of alcohols with hydrogen halides to give corresponding haloalkanes usually proceed reasonably well, but there are problems. Besides rearrangements, there are often other side reactions. Also, those are rather harsh reaction conditions because those are very strong acids, and if there are other sensitive groups elsewhere in the molecule, they could react. So for that reason, we have developed other, better, more selective methods that convert alcohols into alkyl halides through SN2 reaction mechanism, which is particularly important for secondary alcohols because that avoids rearrangements and results in formation of cleaner product and in much better yield. So those would be reactions of alcohols with phosphorus halides and thionyl chloride. So first let's look at the use of phosphorus halides. Phosphorus halides are phosphorus trichloride, phosphorus tribromide, and phosphorus triiodide. Phosphorus trichloride and tribromide are used as such. They're available as such reagents. Phosphorus triiodide could also be used, but it is corrosive and also it's actually a liquid. So it's a little bit difficult to handle corrosive liquid. At the same time, it could be prepared in situ. That means in the reaction mixture from elements. So simply using elements, red phosphorus, that's phosphorus 4, and iodine, and mixing them in appropriate amounts in 3:1 ratio gives phosphorus iodide in solution. So that's usually what we use instead of phosphorus triiodide. So if you see phosphorus plus iodine reacting with alcohol, that means that phosphorus iodide is reacting with an alcohol. And here is the reaction mechanism on example of phosphorus tribromide. So reaction of an alcohol, in this case 1-propanol, with phosphorus tribromide proceeds in such a way that oxygen donates free electron pair to empty d orbital of phosphorus. So we are exploiting the fact that phosphorus is a third row, third period element, and so can expand its octet. Also, phosphorus forms exceptionally strong bonds with oxygen, and so that's something we frequently exploit in organic synthesis. We use phosphorus reagents to form bonds with oxygen because that's thermodynamically favorable process. Those are exceptionally strong bonds, and usually they make then the entire reaction, the entire process extremely favorable. The result is formation of this, what we call Zwitter ion, compound with charge separations. And now phosphorus loses one of the bromines, because even though phosphorus has expanded octet and can expand octet, that's not a stable electronic configuration of phosphorus, and also we have negative charge on phosphorus, and phosphorus is not very good at tolerating negative charge. So the weakest bond to phosphorus breaks, and that's one of the bonds to bromine. Result is formation of, as you can see, oxonium ion, which you already know is a good leaving group, and a nucleophile, bromide anion. So in an SN2 reaction, backside attack of bromide anion nucleophile, leaving group is displaced to give the product. And product in this case is 1-bromopropane. The resulting byproduct is actually acidic. So this compound is, so this is the actual desired product, 1-bromopropane, but byproduct is acidic. And this acid could interfere with possibly other functional groups, or it could even protonate alcohol and cause problems. So frequently we add non-nucleophilic base. Non-nucleophilic base is pyridine, and will react with an acid to form corresponding pyridinium salt. And so that keeps reaction conditions neutral. Note that there are 2 more bromines on phosphorus, so this reaction cycle could repeat 2 more times. So stoichiometry is 3-to-1. 1 molecule of phosphorus tribromide, or trihalide in general, reacts with 3 molecules of alcohol. An alternative reagent for conversion of alcohols into alkyl halides is thionyl chloride or thionyl bromide, depending on whether we want to prepare alkyl chloride or alkyl bromide. And here is one example. So reaction of alcohol, 2-butanol, with thionyl chloride gives 2-chlorobutane. Byproducts are sulfur dioxide and hydrogen chloride. And that's actually very useful because the 2 products are gases, and we can allow them to bubble out of the solution. So that could result in formation of very clean product without a need for purification. All we need to do is evaporate the solvent, and we end up usually with very pure alkyl halide. Here is another example, reaction of cyclohexanol with thionyl chloride. Product is chlorocyclohexane, and again byproducts are sulfur dioxide and hydrogen chloride. Again, they wouldn't present any problem, and we can allow them to bubble out of the solution. But if we believe that hydrogen chloride as an acid could present a problem, we can add non-nucleophilic base that you have just seen, pyridine, and then product is pyridinium hydrochloride. Now in this case then workup and purification is a little bit more involved because pyridinium hydrochloride is a solid, and so we have to separate that from our reaction product. But sometimes we have to use pyridine if we want to obtain desired product, because sometimes starting material may contain functional group that is sensitive to acid and may react with an acid. As you have noticed already, thionyl chloride contains 2 atoms of chlorine, but only one of the 2 atoms is incorporated into the final product. The other one is lost as molecule of hydrogen chloride. Now in this case we have a little bit different molecule. We have 4-pentene 2-ol. So reaction with thionyl chloride actually results in formation of dichloride, and that's because hydrogen chloride adds a cross-double bond following Markovnikov rule, and we end up with formation of dichloride. So hydrogen and chlorine from hydrogen chloride are shown in the product for emphasis. Hydrogen is shown for emphasis. So in this case, if we want to avoid addition of hydrogen chloride across a double bond, we have to add pyridine to the reaction mixture, and that will result in formation of pyridinium hydrochloride, and addition will be avoided. And then product is simply 4-chloro 1-pentene. Reaction mechanism involves an initial addition, nucleophilic addition of oxygen nucleophile to sulfur-oxygen double bond. Sulfur-oxygen double bond is polarized, where sulfur is partially positive, so electron efficient. That means it acts as an electrophile, and oxygen would be a nucleophilic end of the double bond, but in this case that doesn't matter. So oxygen adds to sulfur to form sulfur-oxygen sigma bond, and that results in pi electron pair flowing to the other oxygen of sulfoxide bond. We end up with this intermediate, tetrahedral sulfur intermediate, and just like phosphorus, sulfur tends to form very strong bonds to oxygen. So for that reason, it tends to reform double bonds it used to form with oxygen. So electron pair flows back from oxygen to reform sulfur-oxygen double bond, and simultaneously one of the weakest bonds to sulfur is going to break, and that's bond to chlorine. The result is formation of this actually good leaving group, again oxonium ion, and chloride ion, a nucleophile. So again, in an SN2 process, backside attack of the nucleophile displaces the leaving group. So this is good leaving group here in green rectangle. So attack of the nucleophile results in formation of corresponding chloroalkane, and also, so chloroalkane is desired product, also the byproduct. This byproduct is actually unstable and decomposes into sulfur dioxide and hydrogen chloride. And if we add pyridine, then hydrogen chloride is converted to pyridinium hydrochloride. Now you may have noticed that in all the examples we covered in this video, fluorine is never mentioned. Formation of carbon-fluorine bond is never mentioned. That's because corresponding fluorine compounds, let's say hydrogen fluoride, phosphorus trifluoride, or thionyl fluoride, they don't work in these reactions. So none of these processes is suitable for formation of alkyl fluorides. Alkyl fluorides are actually rather difficult to make, and we need special process for this. You may have heard about thionyl fluoride. It's a gas, and actually it is used to kill termites. So if house is infested with termites, then tent is placed and thionyl fluoride is pumped into it. So highly toxic gas, it will kill anything living, including termites. But it does not work in these reactions. It will not replace hydroxyl group with fluorine. So that's a limitation of all of these processes. We cannot form alkyl fluoride. And this completes our examination of substitution reactions of alcohols. Next, we are going to examine elimination reactions of alcohols.